Here in lectures 23A and 23B, we are in the heart of the course, Differential Equations and Linear Algebra. We've been looking at eigenvalues and eigenvectors, both linear systems of differential equations, and a little bit and more now here in lecture 23B with linear systems of difference equations. 23A, we look at complex eigenvalues and eigenvectors. We've been looking at real eigenvalues and eigenvectors for two-dimensional linear systems of differential equations. Instead of getting straight line solutions, we get spiraling behavior. We're going to look at spiral sinks and spiral sources. There's also something called a center that I'm not really going to focus on in this lecture. It will come in the next lecture. All right, so let's look at some examples. This is going to be a spiral sink example. Actually, this example will be in enough detail that we won't have time to do a spiral source example, but I will indicate what would happen with the spiral source example. So here's our linear system. Looks like a pretty ordinary looking linear system. Here's our coefficient matrix, -1, -2, 2, -1. It's tempting to look at that and say, hey, there are a lot of negative signs, this must be a sink, and it is a sink, but it's not a spiral sink. So again, don't be too keyed in on the sign of the entries of the matrices. That's not the key thing to look at. Let's do what we've always been doing here recently. Let's find the characteristic polynomial, find the eigenvalues, find the eigenvectors. What happens in this case? Well, here is the characteristic polynomial. Again, as always, it's the determinant of a minus lambda I, which is this. Go ahead and take that determinant. You get -1 minus lambda in parentheses times -1 minus lambda in parentheses again, minus the product of 2 and -2, which is +4 ultimately. And when you FOIL this out, you get a lambda squared plus 2 lambda plus 1. When we add 4 to that, we get a lambda squared plus 2 lambda plus 5. Now try to factor it. But hey, you're stuck. You can think about this for a while. Unless you have a lot of familiarity with complex numbers, you probably don't know how to factor this. In fact, the quadratic formula gives us a square root of a negative number. Yikes! If you've never dealt with imaginary and complex numbers before, you don't know what to do. Well, now I'm going to teach you what to do, so hang on here. How do you deal with square roots of negative numbers? What do we do now? First, we introduce something called the imaginary unit. We define I to equal the square root of -1. In other words, I is the solution of, well, one solution of this equation, x squared plus 1 equaling 0. In other words, x squared equaling -1. And if you've never dealt with imaginary or complex numbers before, you'd be screaming your head off here right now, saying, hey, there are no solutions to such an equation, because when I square numbers, I can't get a negative number. Is it legal to do this? Is that okay? Well, we can be like Darth Sidious. What would Darth Sidious say in this situation? From Star Wars, he would say, I will make it legal. That's what Darth Sidious would say. And I'm being serious. That's what we're going to do. We're going to make it legal. There is no problem with existence of this number here. Imaginary, this is the imaginary unit. People call it imaginary because they thought, hey, it didn't exist. But then people found that it had uses. It is a good idea. There's no problem with existence. We can define imaginary numbers and the corresponding complex number system. It is a perfectly legitimate number system. The only question is, the only real question, pun intended, is whether it is useful or not. That's the only question. What is an arbitrary complex number? An arbitrary complex number has the form some real number, A, plus some other real number, B, times this imaginary unit I. And by the way, the imaginary unit I has nothing to do with I hat, the standard unit vector in the horizontal rightward direction. It has nothing to do with that. It is the imaginary unit here, the square root of -1. When I square I get 1. Excuse me, -1. -1. I can certainly write symbols like this, and I can certainly define what it means to, for example, add complex numbers. For example, if I'm going to take 2 plus 3i and add 4 minus 7i to that, the A, that real number, is called the real part of the complex number, and the B, which is a real number, is called the imaginary part. Even though it's a real number, that's real important to keep track of. What you do when you add complex numbers is do the same kind of thing you do when you add vectors. Add, well, real part by real part, imaginary part by imaginary part. It's analogous to adding vectors component-wise. We go 2 plus 4, add the real parts, plus, now add the imaginary parts, 3 plus negative 7, which is, of course, 3 minus 7, but that's an imaginary part. We need to put it next to the I. Simplify, you get 6 minus 4i. 3 plus negative 7 is negative 4. I can think of that as 6 plus negative 4 times I, but of course I could write that as 6 minus 4i if I like as well. You can multiply complex numbers. 2 plus 3i times 4 minus 7i. How? Pretend like they're polynomials. Pretend like these are two linear polynomials in I, but then remember that I squared equals negative 1. So you FOIL this, right? FOIL, first, outside, inside, last. First times first, 2 times 4 is 8. Outside times outside is 2 times negative 7i is what you think it should be, negative 14i. Inside times inside is 3i times 4, which is what you think it should be, 12i. And last times last is 3i times negative 7i. That would be minus 21i squared. Replace the I squared with negative 1. That makes this whole thing negative 21 times negative 1, which is positive 21. That's a positive 21 there, is what I mean. 8 plus 21 is 29. Negative 14i plus 12i is negative 2i. And there's the answer, assuming I have not made a mistake. Maybe we should use Mathematica quick to check and make sure I did not make a mistake. So how can I get it in Mathematica? I can use a capital I for the imaginary unit, little I. 2 plus 3i. 2 plus 3, capital I is the imaginary unit in Mathematica, times in parentheses 4 minus 7i. 29 minus 2i, I got the right answer. Very happy about that. All right. So it's a perfectly legitimate number system. We can even divide complex numbers. I'm not going to show you that in this video. I will show you it in later videos. You can even divide complex numbers. And of course you can subtract them. And there's plenty of other things you can do, some of which we're going to see in this video here today. All right? So very, very legitimate thing to do, mathematically speaking. Again, the only real question is it useful? It's certainly fun, but is it useful? Let's keep going with this. So what would this particular matrix, what would its eigenvalues be as complex numbers? Remember I had the quadratic formula. Right there, I wrote the answers as negative 1 plus or minus square root of negative 16 over 2. That comes here now. How can I simplify this? Well, negative 16 is negative 1 times 16. And assuming square roots obey similar laws as real numbers, or maybe better, defining them to obey similar laws as real numbers, I can say the square root of this product is the product of their square roots. Square root of 16 is 4. Square root of negative 1 is I. And then simplify. Negative 1 plus or minus 2i seems to be the two eigenvalues. These are called complex conjugates of each other. They are related to each other. A quick drawing illustrates that you can view these geometrically. You can make a plane, and you can label the axes with the words real and imaginary. And you can think of complex numbers as points in this complex plane. Yes, that imaginary axis is there. It's not a figment of your imagination. These are just labels, okay? And I can assign a rectangular coordinate system to this. And for each complex number, I can plot it. Essentially, the first coordinate is the real part, and the second coordinate is the imaginary part. And again, when I say imaginary part, I mean the number that's next to the I, which is a real number, not the I itself, or not the combination itself. So negative 1 plus 2i could be plotted in this complex plane right there, negative 1 plus 2i. And its complex conjugate, negative 1 minus I, where you switch the sign of the imaginary part, would be down here. This is negative 1 minus 2i. And these complex conjugates are symmetric across the real axis. They are equidistant from the real axis and on the same vertical line. And that will always happen. The complex conjugate of an arbitrary complex number, written with a bar over it typically, is a minus bi. A plus bi is the original complex number. I put a bar over it, that means complex conjugate is a minus bi. Keep in mind if b is negative, then negative bi would be plus some positive number times I. What in the world does this mean? Should we find the corresponding complex eigenvectors too? And I guess they would have to be complex eigenvectors, wouldn't they? And if we do that, remember what our purpose is. Our purpose is to draw the phase plane, and the motivation for eigenvalues and eigenvectors was straight line solutions. So are there imaginary straight line solutions in the phase plane? This is unclear. This is maybe very confusing. Hopefully we can dispel the confusion. We're getting there. Just hang with me. Just think of it as fun here initially. Let's go ahead and take one of these eigenvalues. E values is short for eigenvalues. E vectors will be short for eigenvectors, and E spaces will be short for eigenspaces, I guess. And altogether, I like to call them E stuff for eigenvalues, eigenvectors, and eigenspaces. It's a bunch of E stuff. See if there's a corresponding E vector, eigenvector. So what do? Do the same thing we've always done. Put these things in the matrix, A minus lambda I. Remember what A is here. A was the matrix, -1, -2, 2, -1, a real matrix. A minus lambda I, therefore, is -1 minus lambda in the upper left, -2 in the upper right, +2 in the lower left, and -1 minus lambda in the lower right, as we saw before. Now go ahead and plug in lambda equals, I took -1 plus 2i, I also could do -1 minus 2i, but anyway, here we go, plug it in. Oh, simplify, what's this? I guess -1 minus -1, -1 minus -1 is -1 plus 1 is 0, but then I get a -2i. Yeah, it simplifies to -2i, which is what's called a purely imaginary number. It's on the complex plane there, it's on that imaginary axis. By the way, every real number can be thought of as a complex number. Any real number A can be thought of as A plus 0i. So you can think of the real number system as this horizontal axis embedded in the complex plane. Do the same thing down here. What do we have? We've got, well, we're thinking about row operations here, ultimately. We are talking about the corresponding homogeneous system because we're trying to find the eigenvectors, and there are going to be non-zero solutions to that corresponding homogeneous system. Doesn't look like these are necessarily multiples of each other as we've been encountering with eigenvalue calculations, but that's a bit deceiving. They actually are. How can we verify that? Well, one thing we could do is we could try to make this become a 1 like we usually do. So I can divide the top row by -2i. -2i divided by -2i should be 1, and it is. So I get a 1 right there. But if I do it to the first entry, I have to do it to the other entries. 0 divided by -2i is still 0. What's -2 divided by -2i? I claim it's 1 over I, and I claim that equals -i. What? That's kind of weird. -2 divided by -2i, I guess it makes sense since the -2 should cancel, that this should equal +1 over I. The -2's cancel. But why should +1 over I equal -i? Be the additive inverse of I. Well, you can do a little trick calculation. You can multiply the top and bottom of this fraction by the complex conjugate at the bottom. Now that number is a purely imaginary number. It's 0 plus 1 times I. Its complex conjugate would be 0 minus 1 times I, -i. And so on top you get a -i, and on the bottom I guess you get a -i squared. But hey, if I squared is -1, that would mean -i squared, parentheses for extra emphasis, is negative of -1, which is +1. That's what I mean here when I write -i squared, is I mean this. Do the I squared first, then put the negative sign. That's a 1. This is -i divided by 1. This is -i. Weird, but true. 1 over I. The multiplicative inverse of I is -i. It's additive inverse. Weird. Wild, amazing, but true. And once you've got it like that, then you can see these two rows are constantly multiples of each other. The second row is twice the first. Hey, it worked. And I get a row of zeros now when I multiply row 1 by -2 and add it to row 2, get a row of zeros. Just like we always have been with complex, with eigenvalues and trying to find the corresponding eigenvectors. And I guess this would be equivalent here to the equation x minus iy equals 0. So x would be I times y, and if y is a free variable, and I pick it to be, say, 1, like that, I guess that means x is I times 1, x is I. Oh, we got a complex eigenvector. Whoa, I put the question marks there because, again, it's still just weird. Like, what do we do with this? Yes, it is right. There's no algebra mistakes here. But how do you make sense out of all this? Hang on, we're working our way toward it here. But maybe before we try to work through it algebraically, maybe we should take a step back and say, hey, we have qualitative techniques. Our original system is a real system, no imaginary or complex numbers, or, I mean, the real numbers are complex numbers, but you get what I mean. We should be able to draw a phase plane. We should be able to use qualitative techniques, make a phase plane, draw nullclines. Yeah, the x nullcline is this. I erased the matrix. Write it again here. A had first row equal to -1, -2, and therefore the x nullcline is -x minus 2y equals 0. Solve that for y as a function of x. You get a line with the slope of -1/2 through the origin. And the y nullcline is this. The second row of A was 2, -1. 2x minus y is 0, so y is 2x is the y nullcline. That's a line through the origin with the slope of 2. Interesting. The slopes of these lines are what are called negative reciprocals, and that means these lines, these nullclines, are actually perpendicular to each other, orthogonal to each other. It doesn't always happen with complex eigenvalues, but it is happening here. And here's the phase plane. And remember my color coding. Well, first of all, let's look at the nullclines. The brown line here, that's y equals -1/2, that's the x nullcline, so solutions have to cross that vertically, going down over here and up over there, evidently. And the x nullcline is the pink line, y equals 2x, solutions have to cross that, that's the y nullcline, solutions have to cross that horizontally. Horizontal tangents, as you can see, is happening here. And notice my color coding, although I did make the color coding better than lecture 22A, because it was hard to tell the distinction between the light blue and the light green. I'm sorry about that. So I made my green brighter here. Light red or pink represents northeast motion. dx dt and dy dt are both positive. Light blue represents northwest motion. dx dt is negative, dy dt is positive. The green represents southwest motion for solution curves and vectors in the vector field. dx dt and dy dt are both negative, and yellow represents southeast motion. dx dt is positive, dy dt is negative. dx dt is positive, rightward motion in pink and yellow, negative, leftward motion in blue and green. dy dt is positive in pink and blue regions, and negative in yellow and green. And again, we're going to try to stay consistent with this coloring for the rest of the semester here. Isn't that pretty? And yeah, it looks like there are no straight line solutions. There is an equilibrium point at the origin, it's unique because, remember, the matrix A has a non-zero determinant. The determinant of this is going to be 1. Minus -4 is 1 plus 4 is 5, non-zero. So there's a unique equilibrium point. These nullclines are distinct lines. They intersect at just one point at the origin there. And yeah, there's no straight line solutions. All these solutions are curved. But at the same time, where are the complex numbers? There are real solutions. It seems, spiraling in toward the origin. It's a spiral sink. What fun. The water is not only going down the drain, but it's spinning around the drain as it goes. So what do? We can try guessing. I mean, there's oscillation going on. Maybe we should use cosines and sines. But those oscillations evidently are getting smaller and smaller in amplitude. So maybe we should throw in an exponential decay. And yes, that can work. But complex numbers have the benefit of making the calculations actually a little quicker in the big scheme of things. And later on, we're going to see they have the benefit, some other benefits. We get to chapter 4 of complex numbers. And the key to relate the complex numbers to the real numbers is something called Euler's identity. More science fiction fun here. If you were abducted by aliens and they said, well, they'd let you go if you told them the most beautiful equation in the universe, what would you say? Maybe all my viewers, for the most part, might know, because you like math so much. In case you don't, I've got your ticket to freedom. Here it is. E to the I pi plus 1 equals 0. There's the most beautiful equation in the universe, and they would agree with you and they'd let you go, assuming they understood what you said. Why is that the most beautiful equation in the universe? It's got the 5 most important numbers in it. 0, 1, e, I, and pi are the 5 most important numbers. Wait a minute. Wouldn't a physicist disagree and say c and h bar are more important? Hang on there. C and h bar. C is the speed of light. H bar is Planck's constant, maybe divided by 2 pi, I forget. Those are physical constants. Did you know physical constants are not numbers? Did you know that? They're not numbers. 0, 1, e, I, and pi are numbers. But why aren't physical constants numbers? Because their values depend on the units you use, that's why. They're physical constants. The value you use for the physical constant depends on the unit system. That's why they are not numbers. Moreover, we've got the 3 most important operations: addition, multiplication, I times pi, and exponentiation are the 3 most important operations. And the most important equivalence relation. Hey, I talked about equivalence relations in lecture 22b with similar matrices. Equals is the most important equivalence relation. By the way, some people write this as e to the I pi equals -1, but I think it's much more beautiful to write it this way, because then you can emphasize 0 and +1 as being part of the equation. But this is just a special case of Euler's identity. There's a couple Euler's identities out there, actually. One of them is related to discrete math, graph theory, and also related to topology. This Euler's identity is more of an analytical kind of thing, an equation involving these kinds of functions. Here it is, e to the I theta equals cos theta plus I sine theta. Exponential functions are related to trig functions when you use imaginary complex numbers. Wow! It's right. Believe me, it's right. Why is it true, though? Some people just take this as a definition, but that's kind of silly in a sense. We could, and we will right now, use Taylor series, and more practice with Taylor series, like we did recently with the matrix exponential, to do a hand-wavy, non-rigorous justification. And I'm going to show it to you here, though it may not be super satisfying. Why not? Well, to the mathematicians out there, it's not super satisfying because we're not going to justify the calculations we do. They involve infinite series and rearranging infinite series, and we're not thinking about questions of convergence or anything like that. But to the scientists and engineers out there, it's nice symbolically speaking, but it doesn't give you any intuition as to why it works. If I have time, maybe lecture 24a, I might show you some intuitive pictures to help you believe it more thoroughly, you might say, even though the intuition still maybe will not quite be there. Here it is. First of all, use the Taylor series for e to the x when x is real, and assume it works when x is I times theta, where I is the imaginary unit. What was the Taylor series? It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot 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 forever and ever, and it converges for all x to e to the x. Just replace all those x's with I times theta. 1 plus I theta plus I theta squared over 2 factorial, which is I squared theta squared over 2 factorial, by definition of multiplication here. X cubed over 3 factorial becomes I cubed theta cubed over 3 factorial. x to the 4th over 4 factorial becomes I to the 4th, theta to the 4th over 4 factorial. X to the 5th over 5 factorial becomes this, etc. forever and ever. Then use the fact that I squared is negative 1. So I guess that means I cubed is negative 1 times I. That's negative I. Interesting. 1 over I equals negative I, but so does I cubed. Yes, it does. It really does. Wow. I cubed is both the additive inverse of I and the multiplicative inverse of I. Wild. I to the 4th, I guess, would be I times negative I. Negative I squared. Negative, negative 1, positive 1 is what I to the 4th equals. So I guess that would mean I to the 5th is back to I. Wild. That's called group theory. These things generate a cyclic group of order 4. I do want to talk about group theory with flows too, but okay, at the moment we're not going there. So replace I squared with negative 1 to get that negative sign there. Replace I cubed with negative I to get the negative I there. Replace I to the 4th with 1 to get 1 theta to the 4th over 4 factorial there. Replace I to the 5th with I. Rearrange. Group the terms that don't have any I together, which are all even powers of theta. Group the terms that do have an I next to them together and factor out the I. Those are all the odd powers of theta. And hey, if you know your Taylor series, you know this is cos theta and this is sine theta. Done. Fun, fun, fun. All right. So symbolically it's kind of fun, but again, it may not be completely satisfying, but we will use it, okay? How is this related to differential equations, though? How is this helpful? Here's the key thing, one key thing at least. Since the purely algebraic properties, which are called field properties, of the complex number system are the same as those of the real number systems, which means things like commutative property, both addition and multiplication, associative property, existence of additive and multiplicative inverses, that kind of thing, are all the same. The calculations are a little trickier and complex, but they're still the same formal properties. This function, where I do the same thing I did with the real solutions, when we had non-spiral sinks and sources and also saddle points, I took e to the eigenvalue times t times the corresponding eigenvector. In this case, to get that, that should still be a solution to the differential equation. I will try to justify this more in a bit here. What's the connection, though, to real solutions? Euler's identity allows us to connect the two. It allows us to do the following calculations. There's where that comes from. And hey, I can distribute the t through here and get e to the negative t plus 2it. And shouldn't I be allowed to say that equals e to the negative t times e to the I times 2t? Yeah, and that's essentially by definition that works. But then Euler's identity says now make that replacement. Okay, fine. And this is one big complex scalar. Go ahead and multiply times this complex vector to get a new complex vector. The first component comes from multiplying all this times I. I squared is negative 1, therefore I get a negative in front of the sine term. Don't forget the e to the negative t. The cosine term doesn't have an I, so the I gets kind of attached to it. I get this I e to the negative t cos 2t. Also multiply by 1 for the second component, and so you get the exact same thing that I have over there, because I'm multiplying it by 1. Okay, fine and dandy. A little rearranging as we often do. Allows us to group together the parts that don't have an I, these things, and the parts that do have an I. And for those that do have an I, factor out the I. Get that. Double check it. Yeah, looks good. And that's not a complex number, but it's a complex vector. It's got a real part and an imaginary part. The imaginary part is real still. It's just the thing next to the I. That's the real part. That's the imaginary part. RE means real, IM means imaginary, but again, the imaginary part is a real quantity, a real vector in this case. It's just next to the I. That's why we call it the imaginary part. Not only do we have complex numbers, we have complex vectors. I wonder if we got lucky here. I wonder if YRE and YIM might solve the original ODE. After all, they involve trig functions with exponential decay, just like we were guessing. I feel really excited. A little extra hyper. By the way, I was really tired about an hour ago, but I don't know, have some extra sugar or something. Check it. Let's check the real one. In the ODE, take its derivative. Take the time to double check that. You need the product rule. Let me quick double check it here. I got a first function and a second function. This is the derivative of the first times the second, plus the first is negative e to the negative t, so I get the negative sign there, times the derivative of sine 2t is going to be cos 2t times 2. Yep, okay. Here we also have the product rule. Yeah, that's right. Okay, that's the derivative of the real part of the complex solution. The C, by the way, here stands for complex solution. And plug it into the right-hand side of the differential equation. A times y is the matrix A times this vector. Do the multiplication, and lo and behold, you do get the same thing. This matches this. Double check it. Yeah. Yep, they match. It's a solution. It worked. Turns out YM works too. You can check it. This one. Cool. And no imaginary numbers there anymore. One big mistake many students make is they continue to use the imaginary numbers at this point. Don't use them anymore. We are now free from imaginary numbers from this point on. What's the general solution? We've got two linearly independent solutions of the ODE. Two linearly independent real solutions of the real ODE. Therefore, by the theory, since the solution space is two-dimensional, I haven't written the theorem for that down yet, but I've always been emphasizing it. It's a two-dimensional linear system. The solution space as a vector space is two-dimensional. Got two linearly independent solutions to the system. Therefore, the basis theorem implies they span the solution space, and therefore are a basis for the solution space. And that means the general solution is an arbitrary linear combination of them. There we have it. No imaginary numbers anymore. Yeah, I taught this course plenty in terms of just differential equations before, and one big mistake is people still sometimes put i's in there. We are past the i's now at this point. It was just a tool to help us get to this real solution. Let's solve an IVP. This particular example works out nicely because it's super easy to solve for K1 and K2. They don't always work out this nicely. Since sine of 0 is 0 and cosine of 0 is 1 and e to the 0 is 1, simplifies to the first component equaling K2 and the second component equaling K1. So our unique solution to the initial value problem with this initial condition, 1, 2, is that function, assuming I have not made a mistake. And we can graph it in the phase plane. There it is. The initial point is at the point whose coordinates are 1, 2. 1, 2. The t means transpose, so I'm thinking of y0 as a column vector by writing the transpose there. For t greater than 0, this heads toward the origin. It decays toward the origin, which makes sense in an oscillatory way because of the trig functions and because of the exponential decay of them. You could graph this as t decreases as well, backwards time. It would go off to infinity in backwards time, keep spiraling bigger and bigger. But usually you think about letting time run forward, so we call it a spiral sink going toward the origin. Very nice. Why does this all work? Just a couple more slides here. Well, first let's take a step back, and consider the real case. Suppose lambda is a real eigenvalue for A with non-zero real eigenvector V. why does this kind of function solve the differential equation? We haven't talked about that yet. I just said do that to this point. Well, as always, left-hand side equals right-hand side. Check it. Here's the left-hand side when you substitute because of the chain rule. Differentiate this. V is constant, lambda is constant. The V stays as is. Differentiating e to the lambda t with respect to t gives you an extra factor of lambda. There we have it. That's what the left-hand side simplifies to. On the other hand, the right-hand side, a times y, plug in the function e to the lambda t times v, and use the fact that lambda is an eigenvalue and v is a corresponding eigenvector, as well as the associative property. I can factor out the e to the lambda t in front to get that. It's a scalar. Got a times v. V is an eigenvector for the eigenvalue lambda right there. And then by the associative and commutative property, I can rewrite it like that. And this matches that. Yes, they're solutions. But what about the complex case? These purely symbolic calculations here still work because, again, the complex number system is a field. And because of how we define derivatives of complex functions and complex functions times vectors, I can still differentiate like this, even when lambda is a complex number and v is a complex eigenvector. And I can still multiply them by the matrix this way. The properties still work. But there's still one more key property. We need to separate what it means in terms of real and imaginary parts. Two complex numbers, in fact, are the same. I write C or A plus BI equals C plus DI. That one equality is equivalent to two equalities. A equals C and B equals D. Just like with vectors. Okay? And that's what we need here. And by definition, when we differentiate this, we differentiate the real part and then add I times the derivative of the imaginary part to get this. And when you multiply times a matrix, you do distribute the matrix through to get this, and you can factor out the I in front of the matrix. All the things you would hope to be true symbolically are true. Two complex quantities, like I just said, are equal if and only if their corresponding real and imaginary parts are equal. We therefore conclude that Yre prime equals A times Yr of t, and Yim prime, since it's next to the I, is A times Yim of t for all t. And there's a typo there. I forgot to change this to the IMs there. It's all pretty nice. And it has real implications for systems, and therefore real implications for applications too. Like to masses on springs, where the damping is not super strong. It's weak enough that you still get oscillations, but the oscillation is decreasing in amplitude. That's what this models, for example, or what it can model. This is our last slide. Let's summarize the behavior based on eigenvalues. This is not a complete summary. This is partial. These are the main cases. One case that's going to be missing is this center idea that I mentioned before. There's some other cases that are missing as well. Like what if you just have a single real eigenvalue, but it's a double root? And also, what if 0 is an eigenvalue of A? Those are the cases I'm avoiding at the moment. For a two-dimensional system, where we have an arbitrary 2x2 linear system of differential equations, what's the characteristic polynomial? It's this. You check all this. Some shorthand here. This is typically written like this in our class here. Notice AD minus BC, AD minus BC, that's the determinant of the A. And it is the constant that you put at the end in the characteristic polynomial. I don't know if you've noticed that so far, but it's true. And it does equal the product of the eigenvalues. If you factor it in terms of the eigenvalues here, lambda minus lambda 1 times lambda minus lambda 2, FOIL this out, the product of lambda 1 and negative lambda 1 and negative lambda 2 would be lambda 1 times lambda 2, which would have to equal this, the constant term, the determinant, like I mentioned recently, lecture 22b. The product of the eigenvalues is the determinant of the matrix, and that's why I'm calling it D. Shorthand here. I also have this minus A plus D in here. This A plus D I'm giving a name as well. I'm calling it T. D stands for determinant. What does T stand for? It stands for something called the trace of the matrix. A plus D, it's the sum of the numbers in the main diagonal. That seems special, right? Main diagonals are special. Add them, I get this thing called the trace of the matrix, and it is, well, negative the trace is the coefficient of lambda in the characteristic polynomial. Guess what? You no longer have to go through this calculation again unless I ask you to. You can jump right from the matrix to the characteristic polynomial because you know the lambda term is negative trace times lambda and the constant term is the determinant. Save time and work when you do that. And yeah, in theory I can factor this. Even if lambda 1 and lambda 2 are complex numbers. Although I will tell you, if A, B, C, and D are real numbers, as we've been doing, as we will continue doing, lambda 1 and lambda 2 will be complex conjugates of each other. When A, B, C, and D are real in the matrix there, if these are all real quantities, real entries to the matrix, A, B, C, and D are real, then it turns out that lambda 2 is the complex conjugate of lambda 1 if they're complex. That even technically works when they're real because the complex conjugate of a real number is itself, excuse me, no, it doesn't work. Sorry. If the eigenvalues are not complex numbers, excuse me, are not real numbers, not real numbers. I mean, real numbers are complex numbers, but there's plenty of complex numbers that are not real numbers. Then lambda 2 is the complex conjugate of lambda 1, and also lambda 1 is the complex conjugate of lambda 2. Just like for our example, we got negative 1 plus or minus 2i. Doesn't have to be the case, and usually not the case when you've got real eigenvalues. Then we can say, real quick summary, the origin is a real non-spiral sink if and only if, shorthand for if and only if is IFF. That means not if, but if and only if. If what? The eigenvalues have to be negative real numbers, yeah. Both of them. The origin is a real non-spiral source, as we saw before, if and only if they're both positive real numbers. How about a saddle point? We saw an example of that. One was positive, one was negative. They're real numbers with opposite signs. Lambda 1 might be less than 0 and lambda 2 would be positive in that case, or lambda 1 could be positive and then lambda 2 would be negative. So I'm not putting inequalities here. They're real numbers with opposite signs. And I guess that means I'm taking neither of them to be 0. Well, is 0 positive or negative? It's sort of its own special case. Though negative 0 does equal 0. The origin is a spiral sink. Our example was a spiral sink. What were the eigenvalues? Negative 1 plus 2i and negative 1 minus 2i. And if you think about the exponential that came from Euler's identity, we got an e to the negative t. That negative t came from the fact that the real part of the eigenvalue was negative 1 when we did the Euler identity. So it's the real part of these eigenvalues that must be negative, and they're going to be complex conjugates of each other. If one has a negative real part, the other one does. Just like our example, negative 1 plus or minus 2i. Negative 1 is the real part for both. I haven't done an example, but it will be a spiral source if and only if these are complex numbers with positive real parts. And I could quickly make such an example by negating the previous example, taking all the entries and negating them, taking their opposites. And that would be a spiral source. And the eigenvalues in that case would actually be positive 1 plus or minus 2i. You might want to check that. The case of complex eigenvalues, The periodicity of the trigonometric parts of the solutions is 2 pi divided by the absolute value of the imaginary parts. For our example, the eigenvalue is -1 plus or minus 2i. That 2 that's in front of the I, or plus or minus 2 I should say, is the imaginary parts of the eigenvalues. Its absolute value is positive 2. We've got a cosine of 2t and a sine of 2t in the equations. The periods of those trig parts would be 2 pi divided by 2 pi in this case. In the phase plane, we did the spiraling. I forgot which direction it went. I think it was, I forgot. Spiraling, I think it was this way. And it doesn't come back to where it starts. It's not an exactly periodic function because of the exponential decay. But it comes back to the same line through the origin from where it started after pi units of time. And that is the end of lecture 23A. Thanks for watching.